In this video, I want to talk about uncertainty and how uncertainty can propagate through calculations to calculated values. So let's say we measured a speed of, say, 15.6 meters per second, but it has some uncertainty associated with it, given here by 0.2453 meters per second. Now this would not be an appropriate way to report this answer, because that uncertainty has way too many significant figures associated with it. We have no reason to quote a uncertainty to 4 significant figures. So if we're going to quote an uncertainty, we should always quote it to generally about 1 significant figure. That's pretty typical. There's rare circumstances where you want to quote more than that. As another example of a measured value, so here we have another speed, 423.1 meters per second, plus or minus 10 meters per second. So here we're still quoting that uncertainty to 1 sig fig, as long as that 0 is insignificant here. But the quoted value for the average, however, has way too many significant digits considering the uncertainty. And so we should match the reported average value or measured value in terms of the uncertainty. And so we should round that to 420 meters per second, plus or minus 10 meters per second. So these would be appropriate quantities to report for a measured value with its uncertainty. And I want to introduce 2 ideas associated with that uncertainty. So there's the absolute uncertainty of a measured value. So this is the thing that follows the plus or minus. So in this case, 0.2 for V1 is the absolute uncertainty. And it has the same units as the quantity that you measured. Then there's also the relative uncertainty, or sometimes called the fractional uncertainty, where we take the uncertainty and divide it by the measured value itself. This tells us how large the uncertainty is relative to the actual measured value. So in this case, we get 0.013, or converting that to a percentage, we could see that that uncertainty is about 1.3% of the measured value. Let's say we have 2 measured values, in this case 2 measured momenta, and we want to add or subtract them. If we want to add the values, of course we just add the central values, P1 and P2, to get the total momentum. But if we want to figure out the uncertainty in the total momentum, we add their absolute uncertainties, we say in quadrature, by which we mean we just add them as if they were the legs of a triangle. And we're usually just using Pythagorean theorem. So I would take delta P1 squared plus delta P2 squared, and then square root that for the uncertainty of the sum of the 2. So I would get something like this. If I were to take the difference between 2 measured values, I would do actually the same thing. The uncertainty in this quantity that I'm calling Q here would again be the uncertainty in P1 squared plus the uncertainty in P2 squared, and then take the square root of that whole thing. Now you have to be a little careful when taking the difference between measured values, because when you take the difference between measured values, well, in this case, the difference between those measured values is a really small quantity, negative 0.08 kilograms per meters per second. But the uncertainty is the same as if you had added them. And so the uncertainty is actually quite large compared to the value itself. We see here there's a relative uncertainty of about 75%. And so one also often has to be very careful in taking the difference between measured values because of this problem. What about if you multiply or divide quantities? So let's say I have a mass and a speed quantity measured here with their uncertainties, and I want to know the momentum, the calculated momentum for these quantities. Well, the momentum itself would just be mass times speed, mass times velocity. The uncertainty in the momentum, well, it's actually easier to write it as the relative uncertainty in the momentum, because it turns out when you multiply or divide quantities like this, you just add the relative uncertainties in quadrature. So you take the relative uncertainty in the mass, delta m over m, and square that, and add that to the square of the relative uncertainty in the velocity, delta v over v. So in this case, you get delta p over p is 0.016 for its relative uncertainty, and so the momentum will be 67 kilograms meters per second, and its uncertainty would be 1 in this case. But more generally, if you have a more complicated looking function that's not just adding, subtracting, multiplying, or dividing, but instead has powers of a quantity, then we need to do a little bit more work. So, for example, if we wanted to calculate kinetic energy from some measured values, so we have a 20 kilogram object and it has a velocity with some uncertainty associated with it. We want to know the kinetic energy and its uncertainty. The kinetic energy is just 1/2 mv squared, but how do we get to the uncertainty of the kinetic energy? Well, if you have, in general, some function of x, of a measured value x, the central value is, of course, you just plug that measured value into the function, get the central value. If you want to understand uncertainties, then what that means is you're taking small variations about that central value, and then that's giving you small variations in the function. Well, that looks a lot like calculus, and in fact, calculus is going to be what helps us here, which is that the uncertainty in the function itself, delta f, is the derivative of the function with respect to the variable x times the uncertainty in that variable x. Okay, so what does that look like in this case? So for a kinetic energy of 1/2 mv squared, I can calculate that kinetic energy for this example. I get 294 joules. The uncertainty in the kinetic energy will be the derivative of the kinetic energy with respect to velocity times the uncertainty in the velocity. Well, dk dv is mv, so it was 1/2 m and then 2 times v, because the 2 came down because I took the derivative. The 2's cancel, I just get mv times the uncertainty, delta v. So I can calculate that uncertainty by plugging in the measured values for m and v, and then the uncertainty for delta v, and I get an uncertainty in the kinetic energy of 1 joule. So the kinetic energy in this case would be 294 plus or minus 1 joule. What if we have multiple variables? Well, if you have multiple variables that have uncertainties inside of them, and you still want to calculate a quantity, well, you can do something very similar. So let's say, again, we're calculating kinetic energy, but now both mass and velocity have uncertainties associated with them. Well, you could do the same thing. So now, if you have, in general, some function that's a function of x and y, two quantities with their own uncertainties, then the uncertainty in that function is the uncertainty of each variable and then added together in quadrature. So you take the partial derivative of f with respect to x times its uncertainty delta x, square that, and add that to the square of the associated uncertainty in the y direction. So let's see what that looks like in the kinetic energy example. In the kinetic energy example, we would take partial k partial m times the uncertainty in m. Well, partial k partial m is just 1/2 v squared. So I put that in for that. And then I would have to multiply that by the numerical value of the uncertainty, delta m. And then partial k partial v is mv. So I would put that inside for that part of the expression. And then I can just put in my measured values and my uncertainties. And ultimately, I will get 2 joules for the uncertainty delta k. So the quantity that I would report would be 332 plus or minus 2 joules. Let's just use these rules of propagation of uncertainties and errors for deriving the common formulas that we know and love. So let's say addition and subtraction. Well, in addition and subtraction, my function f of x and y is just x plus y. So you can imagine using this general formula, delta f, in terms of the addition of the quadratures of the individual functions. And I would get, well, delta x is just 1. Delta f delta y is just 1. And so it turns out I get that the uncertainty in my function is just the sum of the quadratures of the individual variables. And that's what I would have expected already for addition and subtraction. What about multiplication and division? Multiplication and division, again, this is a function of two variables, x and y. And so I can take their partial derivatives. Partial f partial x is actually y. Partial f partial y is now x. Right, it kind of flips. And so I can calculate the uncertainty delta f by taking the sum of the quadratures of those partial derivatives. But as we saw before, it's actually much better to calculate the relative uncertainty in the variable f, so delta f over f, because when you do that, then the cross terms kind of vanish, or cross dependencies vanish, and you just get the sum of the relative uncertainties in x and y in quadrature. You can also use this to derive what the uncertainty is when you have a function which is just a variable multiplied by a constant, because the uncertainty in the function f is now just df dx times delta x. And that means you're just going to take the constant c times the uncertainty in the variable x. And so whenever you're multiplying by a constant, you just multiply the uncertainty by that constant as well. Finally, let's just do some reasoning with the idea of relative uncertainty. So again, let's take a function that is the product of x and y. Both x and y have some uncertainties associated with them. So we know that the relative uncertainty in the function f can be written in this way. And let's imagine that the relative uncertainty for the x variable is something like 14%. The relative uncertainty for the y variable is about 0.2%. So if you put these in to this expression and calculate what is the relative uncertainty in the function f itself, then you find that it is almost entirely dominated by the uncertainty in the x variable. And that's not surprising, because when you're taking these two quantities and then squaring them and adding them, certainly delta x over x is a much larger number, and so it's going to dominate the uncertainty. And so when you're doing calculations, oftentimes your results are dominated by the largest relative uncertainty in your quantity, in your measurements. And so that tells you that you want to reduce, say, the relative uncertainty in that quantity first, because you're going to get the most bang for your buck out of that. Okay, so this was a video about propagation of uncertainty and how to use those formulas to calculate the uncertainty in variables given a bunch of measured quantities.